Last time, we met linear maps and dual spaces. Today we study where a linear map sends vectors, and which vectors it crushes to zero. The two words are null space and range. One tracks what disappears, the other tracks what actually gets hit. Very wholesome surveillance. Suppose T is a linear map from V to W. The null space of T is the set of vectors in V that T sends to the zero vector. The range of T is the set of all outputs T of V, where V runs through V. So the null space lives in the domain, while the range lives in the codomain. Mixing those up is how notation starts biting people. First example, project the plane onto the x-axis. Define P of x, y to be x, 0. A point like 2, 2 gets sent straight down to 2, 0. The null space is the y-axis because those are exactly the vectors whose x-coordinate is 0. The range is the x-axis because every output has y-coordinate 0. Second example, send a vector in R2 to the sum of its coordinates. Define S of x, y to be x plus y. The null space is the line x plus y equals 0. The range is all of R because any real number R is hit by the vector R, 0. So this map crushes a diagonal line to 0, but still hits every scalar. Efficient, vaguely unsettling, but linear. Third example, from R3 to R2, forget the z-coordinate. Define f of x, y, z to be x, y. The null space is the z-axis, all vectors 0, 0, z. The range is all of R2 because every pair x, y is hit by x, y, 0. Now I will leave one important fact as an exercise. For any linear map T from V to W, the null space is a subspace of V, and the range is a subspace of W. For the null space, use the one-step subspace test and compute T of U plus CV. For the range, remember that every vector in the range is an output of something. Then use linearity before the notation starts looking offended. Before the main proposition, let us review injective and surjective functions. Injective means no collisions. If two inputs have the same output, then the inputs were already the same. Surjective means everything in the codomain is hit. Equivalently, the range equals the codomain. Today we focus on injectivity. Surjectivity can wait politely in the corner, assuming it can find one. Here is the proposition. A linear map is injective if and only if its null space contains only the zero vector. In plain language, the only vector allowed to disappear is the zero vector. If some non-zero vector gets sent to 0, then the map has already collapsed two different inputs together, that vector and 0. First direction, assume T is injective. Take any vector V in the null space. By definition, T of V equals 0. Also T of 0 equals 0, because T is linear. So T of V equals T of 0. Since T is injective, equal outputs force equal inputs. Therefore V equals 0. So every vector in the null space is 0, and the null space is exactly the set containing 0. Now the other direction. Assume the null space of T is just 0. To prove injectivity, suppose two vectors U and V have the same image. Subtract the two outputs. Since they are equal, the difference is 0. Because T is linear, T of U minus T of V is T of U minus V. So U minus V is in the null space. But the null space contains only 0. Therefore U minus V equals 0, so U equals V. That is exactly injectivity. No collisions survived the null space check. The intuition is simple. A linear map fails to be injective exactly when it crushes some non-zero direction to zero. If a whole line disappears into zero, different inputs collide. Not injective. If only the zero vector maps to zero, then linearity prevents collisions anywhere else. Let us summarize before null spaces start demanding their own zip code. The null space is the set of inputs sent to zero. The range is the set of all outputs actually hit by the map. Both are subspaces. And you get to prove that as an exercise. Education. The outsourcing industry with chalk. Finally, a linear map is injective exactly when its null space is just zero.